As your quiet guide to the night sky, I'm George. For a long time, I've been sharing calm stories about space to help people slow down, feel wonder, and fall asleep peacefully. Tonight on Z Science, we'll drift together into the quiet corners of the universe. Whether your mind is racing or your body just needs rest, these gentle stories of science are here to help you slow down and drift off with ease. If calm science helps you unwind, a like and a subscribe will keep these quiet stories easy to find. Warm thanks to those already subscribed for the steady support. May this tale be soothing enough to invite sleep. If curiosity keeps the eyes open a little longer, let it be a kind exchange. Wakefulness traded for a small, bright truth. Now, hold this gentle question. What secret does a traveler from another star leave behind when it passes by only once? 3I Atlas is an interstellar object born under a different sun, arriving from elsewhere and departing again. Its path is hyperbolic. In the language of orbits, eccentricity greater than 1 means the track does not close. That is the signature of a guest that will not stay. This matters because such a visitor is a physical sample from another planetary system. Its light and its color hint at composition and texture. Its motion teaches how small worlds are made, nudged, and flung free. A few friendly words for the road. Coma is the soft haze that forms when sunlight warms ice and releases gas and dust. Magnitude is just brightness, where smaller numbers look brighter. Non-gravitational nudges are tiny jets of gas acting like quiet thrusters, shifting the course by a whisper. The journey tonight moves simply. Discovery and naming, the rulers and scales that make distance and speed feel human. How surveys notice what barely glows. The minimal physics of gravity and escape. The route and safe distance, brightness, activity, and color. Calm comparisons with the first 2 recorded visitors. Myths kept tidy, possible origins, and the new instruments preparing for the next hello. No rush. Take what lands and let the rest drift past like streetlights on a late train. Imagine a small wanderer crossing a vast room very slowly, almost shyly, and you will have the right beginning for 3 Atlas. It is an interstellar visitor, which simply means it was not made here. It is a body of ice, dust, and rock that formed around another star, or perhaps in the cold suburbs of a system we will never see, and then was tossed clear into interstellar space. After ages of drifting through the dark, it reached our neighborhood and began to write a single line across our sky. That line is the giveaway. Bound objects trace loops. Unbound visitors do not. 3I Atlas is not looping. It is passing through. The plainest description is this. Sunlight warms its surface. Gravity tugs from far away, and motion follows the quiet arithmetic of orbits. If you could step outside the solar system and watch, you would see a wide open curve that never closes, a shape known as a hyperbola. In friendlier terms, think of a pebble that skims a pond and keeps going rather than sinking. The pebble meets the water, leaves a trace, and moves on. In the same way, 3 Atlas skims our planetary pond, feels the sun, bends a little, and continues into the deep. A careful analogy helps the picture settle. Picture a cathedral of gravity. The sun is the great lantern in the center. The planets are slow dancers tied to that light by invisible ribbons. Every comet born here is a regular guest who knows the steps. Into this patient dance floor walks a traveler already on its way somewhere else. It bows to the lantern, arcs politely as etiquette demands, and then walks out the far door. It does not learn the steps. It does not join the dance. That is 3 Atlas, courteous to our sun, but never ours to keep. What do we actually see? In practice, astronomers first notice a moving point of light against a background of stars that do not move from night to night. A survey telescope takes short exposures, one after another, and software compares the frames. Stars stay fixed in their grid. The visitor shifts slightly between images, link enough of these tiny shifts into a track, point another telescope at the same spot, and a path emerges. When the early measurements are fitted with the equations of motion, an important number appears, the orbital eccentricity. If that number is less than 1, the path is a loop. If it is exactly 1, the path is just at the threshold of escape. If it is greater than 1, the curve is open and the traveler is not bound. For 3 Atlas, that key indicator sits comfortably above the threshold. In other words, it is leaving. The light from such a body tells quiet stories. If warming is strong enough, Isis can sublimate, turn from solid to gas, and lift a little dust, making a faint haze around the solid core. That haze is called the coma. With enough dust and gas pushed by sunlight, there can be a slender tail, always pointing roughly away from the sun. Not because motion drags it backward like a scarf, but because light and charged particles press upon the freed material. If activity is weak, or the surface is crusted with less volatile material, the object can look more like a bare rock, only a point of light with no obvious halo. 3 Atlas may look modest to our eyes, yet modest light can carry generous clues. Brightness rises and falls as distance and sunlight change, and as the body rotates. If the shape is not a perfect sphere, and few small bodies are, then different faces reflect different amounts of light. By plotting these small ups and downs in brightness over time, astronomers can tease out the spin rate and get hints about shape. The color of the light, measured through filters, can suggest whether the surface is rich in certain organics or dust types. These are not loud shouts of truth. They are soft hints, collected with patience, and improved as more data arrive, because 3 Atlas is unbound. Its speed feels brisk when compared to comets raised in our own backyard. It carries a memory of its birth system's motion layered on top of the sun's gravity well. That extra motion is why it could approach from a direction and at a pace that look a little unusual if you expect the regular traffic of long-period comets. It is not breaking rules. It is following a different set of starting conditions. The universe never promised that all travelers would enter by the same door. The naming can be read as a story in miniature. The tag tells you two essential truths. It is the 3rd interstellar visitor recognized, and it was first flagged by an automated sky survey called the Asteroid Terrestrial Impact Last Alert System, a network that quietly scans for new moving points every clear night. There is something charming about that. An instrument built to guard our home finds a messenger from another one. Asterisk. A real observation also lives in the details you rarely notice. When astronomers report a detection, they include the exact timestamps of each exposure, the positions recorded in tiny slices of sky, and the brightness to a few decimals. They worry over atmospheric blur, the way a star's image spreads a little in poor seeing, and the tiny biases of a camera's pixels. They cross-check with other observatories to make sure the same moving point is being followed and not a trick of noise. As these measurements accumulate, the orbit solution tightens. An early path can wobble within a wide corridor. With more nights of data, the corridor narrows until the fate of the traveler, bound or not bound, is clear. There is a gentle nuance worth holding. Activity can act like a set of weak thrusters. When gases escape unevenly, they push a little, and that can tweak the path in subtle ways that pure gravity would not. Interpreting those tweaks demands care, because you do not want to mistake a jet's whisper for a grand new force. Likewise, brightness can be deceptive. An object that looks quiet may be active in ways our instruments barely register, and an object that looks lively may simply have a dusty surface that reflects efficiently. Patience and cross-checks are the remedy, not drama. The cleanest and most truthful picture, then, is both simple and generous. 3 Atlas is a small body from elsewhere, most likely icy, following an open path that bends near the sun and does not come back. It glows faintly, perhaps with a soft veil if warmed enough, and its light carries hints about surface and spin. We know it is interstellar because the geometry of its motion requires more energy than a local loop allows. We watch it by watching the way a single point of light refuses to behave like a local. It visits, it teaches, and it moves on. Hold that image the next time you glance at a quiet sky, a traveler, courteous and brief, making a single graceful bow to the sun before the darkness opens again and the long road resumes. Names, in astronomy, are little maps. They tell you where an object fits in the story, who first spotted it, and what kind of thing it is. The designation 3 Atlas carries all 3 clues in a compact line. The letter I stands for interstellar, a category created when the first visitor from beyond the sun's family appeared and needed a home in the naming system. The numeral is a serial counter. The word that follows celebrates the discoverer. Put it together and you have a simple sentence. The 3rd interstellar object confirmed, found by the Atlas survey. Why invent a new letter at all? For a long time, the sky's wanderers fell neatly into familiar drawers. Comets wore tags like C4 non-periodic or P4 periodic, and asteroids followed their own catalog rules. Then came a surprise, an object that was neither a periodic comet returning on a long leash, nor a local asteroid passing through on a closed loop. Its motion said with quiet confidence that it was unbound, an outsider merely visiting. The International Astronomical Union, keeper of the labels, added a new class with a clear flag, I for interstellar. That single character carries a lot of meaning. It tells observers, students, and software that the usual expectations do not apply. The path will not close. The object has no home orbit here. The counter before the letter matters just as much. 1 I, Almua, and 2 I, Borisov, mark the first 2 entries in the new ledger. 3 I, Atlas, adds another point to a tiny but powerful list. With each number, the statistics of interstellar visitors shift from a curiosity to a pattern. The 3rd tells us that the first was not a fluke, and the 2nd not merely a lucky repeat. It hints that such passers-by may be common, enough that modern surveys will continue to find them. In science, 3 is often the moment a trend stops being a campfire story and begins to look like a rule. You can test the final word in the name. Atlas points to the discoverer, the Asteroid Terrestrial Impact Last Alert System. Atlas is a set of wide-field robotic telescopes running night after night, designed to notice small moving things that might wander too close to Earth. Its mission is sober: find potential hazards early. But the same vigilance that guards our planet also makes it very good at catching faint, fast guests. The design is clever. Instead of staring deeply at one tiny patch of stars, Atlas sweeps large swathes of the sky quickly, returns a little later, and checks what moved. Stars sit politely in their places. Intruders shift a fraction of a frame. Software turns those small shifts into an initial track, and humans review the candidates worth a closer look. That workflow explains why the word Atlas deserves its place in the name. A discovery is never just the first click on a screen. It is a chain. Survey telescopes capture the first glimmers. Pipelines filter signal from noise. Astronomers request follow-up from other facilities. Positions and brightnesses are measured again and again. With enough points along the path, the mathematics becomes decisive. You solve for the orbit, and out drops the eccentricity, the number that describes how open or closed the track is. Less than 1 means a loop. Exactly 1 means just at escape. Greater than 1 means interstellar. When the solution settles comfortably above the threshold, the object earns its eye, and the discoverer earns a name beside the counter. There is a bit of poetry in that pairing. Atlas is a mythic figure who holds up the heavens. Atlas, the instrument, holds up a different burden: vigilance. Night after night, it watches for change. Most nights, the changes are localer near-Earth asteroid, a regular comet, a variable star brightening or dimming as usual. Every so often, the pattern breaks. A moving point refuses the usual dance steps, and the orbit wants to be a wide open curve. That is when a dry line in a database becomes a spark for the whole community. Request follow-up, confirm the motion, test the models, and if it holds, write the new name with its telling letter, because 3 Atlas is also observable as a cometary-looking object. You may see it listed in some places with a traditional comet-style discovery tag as well. A reminder that naming in astronomy carries layers. 1 layer for physical behavior, another for orbital class, another for history. None of those alternate labels change. The essential truth signaled by the eye: the interstellar badge does not care whether the surface is quiet or dusty, whether a faint coma is visible or not. It cares about motion and energy, about whether the sun can keep a grip. The importance of the third extends beyond tidy bookkeeping. A trio of interstellar objects let scientists begin to compare. One showed unusual shapes in its brightness changes. Another behaved like a classic comet with a generous tail. A third arrives with its own mix of activity and motion. Even without diving into those specifics here, the message shines through. Nature is varied, and the stream of visitors carries different stories from different birthplaces. Asterisk. The more entries the ledger holds, the better we can estimate how often planetary systems eject small bodies, what sizes they tend to be, and how their surfaces weather the long cold between the stars. Atlas's role also underlines a quiet shift in how discovery works. Once upon a time, many new comets bore the names of patient individuals at eyepieces. Today, a lot of first sightings come from survey machines that never blink and never get bored. That is not a lot of romance. It is a gain in reach. Robotic sentries can scan vast areas quickly, flag hundreds of candidates, and ask the global community for help. The credit line at the end: Atlas acknowledges that modern team designers and engineers to observers and analysts can spot a faint traveler that older methods might have missed. If you were to condense the story into a single friendly paragraph, it would read like this: 3 Atlas declares in 3 neat steps what the object is, where it sits in a very short sequence, and who saw it first. The I says interstellar. The 3 says the third of its kind that met the standard of proof. The Atlas says a tireless survey built to keep watch noticed a tiny motion that meant a guest had arrived. The rest of the science grows from that seed, but the seed itself is already a small marvel, a name that doubles as a map, guiding curious minds from label to meaning without hurry or fuss. Astronomers carry a few simple rulers for measuring the dark. The first is the astronomical unit, the everyday stride of the solar system. 1 astronomical unit is the average distance from Earth to the Sun, about 150 million kilometers. If that size feels too grand, picture the Earth-Moon gap as a pocket ruler about 380 kilometers. The Sun is roughly 400 pocket rulers away. Light covers 1 astronomical unit in about 8 minutes, which is a comforting way to imagine scale. When you look at the Sun's light dancing on water, that light left around the length of a song ago. The second ruler is speed in kilometers per second. Earth orbits the Sun at about 30 kilometers per second. That is not a typo. Each second, our world travels a small commute across space. Big planets farther out move more slowly. Small bodies closer in move more quickly. Interstellar visitors often carry extra motion from their birth systems, arriving at tens of kilometers per second relative to the Sun. These are not reckless speeds by cosmic standards. They are simply the natural result of falling through gravity from very far away. While already moving in another direction, a third measuring stick is brightness on the magnitude scale. An old but clever system where smaller numbers mean brighter objects. A drop of 1 step in magnitude corresponds to roughly 2.5 times more light. A difference of 5 steps adds up to about 100 times. Because of this inverse system, bright Venus can wear a negative magnitude, while faint comets live in the positive teens. Magnitudes look like strange bookkeeping at first, but they allow precise comparisons even when the sky is noisy or the air is unsteady. With those rulers in hand, the word unbound can be explained without drama. In gravity, every orbit is a balancing act between kinetic energy, the energy of gravitational potential energy, the energy of position in the Sun's well-bound objects have a combined energy that is negative overall, meaning they are trapped in the well and move in closed loops, ellipses that repeat. Unbound objects have a positive total energy, a ticket that lets them come in, curve around, and go back out forever. Think of a deep valley with a surrounding ridge. If you do not have enough energy, you circle inside the valley. If you have just enough, you ride the crest and never quite fall back. If you have more than enough, you cross the ridge and keep walking into the next landscape. Unbound simply means there is no return. Eccentricity is the tidy number that tells you which landscape you are in. A perfect circle has an eccentricity of 0. Any ellipse that closes has a value between 0 and 1. A parabola, the exact escape path, has an eccentricity of exactly 1. A hyperbola, the open curve of a passerby, has a value greater than 1. When astronomers fit observations of a moving point, and the solution asks for an eccentricity comfortably above 1, it is the geometric way of saying this traveler will not be staying. For an interstellar object like 3 Atlas, that greater than 1 signature is central to its identity. Let us anchor the distances. Jupiter orbits at about 5 astronomical units. Neptune sails at about 30 astronomical units. The main belt of asteroids lives mostly between 2 and 3 astronomical units. The Kuiper belt extends to roughly 50 astronomical units. Beyond that, the hypothetical Oort cloud may reach out tens of thousands of astronomical units, a halo of icy leftovers. These numbers do not need to be memorized. They are simply friendly pegs to hang ideas on. Inner system, middle grounds, outer frontier, and far cold reservoir. For speeds, a few quiet comparisons help. 30 kilometers per second, Earth's orbital pace, is fast enough to cross a continent in a handful of minutes. The Sun's escape speed at Earth's distance is about 42 kilometers per second. That number matters because it separates bound from free. Any object moving too slowly will be captured into some loop. An object with excess speed at a great distance can swing in and leave again. Interstellar visitors carry that extra, called the hyperbolic excess speed. It is the leftover after subtracting all the pull the Sun can manage. Now fold brightness back in. As a visitor approaches, it receives more sunlight and may brighten. If ice is warm and gas escapes, dust can be lofted into a coma, which increases the reflecting area and raises the apparent magnitude. At the same time, distance still dims everything. Double the distance, and the light spreads over 4 times the area. Astronomers track these competing effects with light curves, plots of brightness over time, to tease apart geometry, activity, and rotation. Even when an object is only a trembling point in a detector, the mathematics of magnitudes can whisper its size, shape, hints, and surface character put together. These rulers turn mystery into measurement. Astronomical units lay out the map. Kilometers per second explain the motion across it. Magnitudes translate faintness into numbers. Eccentricity greater than 1 labels the path as a hello and goodbye. With these scales in mind, the journey of an interstellar wanderer like 3 Atlas becomes less a riddle and more a readable sentence in the sky. Steady and legible even in the hush before sleep. Wide-field surveys are night watchers with a rhythm. They sweep a patch of sky, pause and sweep it again, then again, returning after a short interval to the same stars. That timing is deliberate. Bright points that belong to the background stay fixed from frame to frame. A nearby wanderer shifts slightly, with a handful of exposures spaced by minutes. Software can measure that tiny drift and flag a moving source that barely rises above the noise. It is patient choreography. Look, step away, look again, and compare. The cadence is tuned to catch things that move at earthly speeds through the field of view. Too slow and the object looks like just another star. Too fast and it becomes a faint streak that might be missed unless the system also searches for trails. Modern pipelines do both. They subtract one image from another to reveal fresh changes. They filter out cosmic ray hits and airplane flashes, and they ask a simple question: which dots shifted just the right amount in just the right direction? When several detections line up within a short time window, the software knits them into a tracklet, a tiny arc with a skyplane speed and direction. A tracklet alone is a whisper. To turn it into a sentence, surveys try to find more of them on the same night and on the nights that follow. Link 2 or more tracklets, and you can estimate an orbit even if the uncertainties are still wide. The sky is big and telescopes are busy. So there is a clearinghouse for this effort, the Minor Planet Center. Observers send in time-stamped positions and brightness measurements. The center posts promising candidates on a confirmation page. That page is a quiet alarm bell for the community, inviting other telescopes to look now, not later. because motion quickly carries a faint target away from where you expect it to be. Asterisk. Follow-up comes from all sizes of instruments. Small telescopes with fast cameras can capture fresh tracklets and extend the arc. Medium and large observatories can chase the object with non-sidereal tracking, moving the telescope at the object's rate so the target stays sharp while stars smear into short lines. For very faint sources, astronomers may stack many short exposures, shifting each image before adding it up so the moving dot lands in the same place. This shift and stack method can pull a whisper out of the noise, turning a maybe into a yes. While the world gathers new measurements, mathematicians do what they do best: fit the data. Each fresh position trims the error bars and tightens the orbit. If the path looks like a closed ellipse, the object belongs to our family. If it sits near the razor's edge of escape, more data are needed. If it insists on a wide open curve, the eccentricity climbs above one and stays there. That is the hallmark of an interstellar visitor like 3 Atlas. The conclusion is not declared on a single noisy night. It emerges as independent observers using different instruments and skies arrive at the same answer. There is also a treasure hunt in the past. Once an orbit is sketched, astronomers scour archival images to find pre-Covari's older exposures where the object was present but unrecognized. Each earlier dot lengthens the timeline and makes the orbit solution sturdier. Because modern images are calibrated against exquisite star catalogs, those old positions can be remarkably precise. A single pre-Covari from months earlier can shrink the corridor of uncertainty dramatically. Just as adding a distant fence post makes a winding path suddenly clear. All the while, the same frames used for astrometry, pinning down position, also carry photometry, simple measures of brightness through standard filters. If the point looks fuzzier than nearby stars, that can hint at a faint coma. If brightness rises faster than geometry alone predicts, outgassing may be adding reflective area. None of these signs are taken in isolation. Teams compare notes, check for instrumental quirks, and repeat measurements on nights with steadier air. Surveys deserve their place in the story, because their design invites serendipity. Instruments like Atlas, Pan-STARRS, Catalina, and the Zwicky Transient Facility do not wait for special events. They create the conditions to notice them. Wide fields catch more sky in fewer shots. Rapid repeats build those crucial automated pipelines never get tired of blinking frames. And global coordination turns a local hint into a worldwide campaign. With observatories trading clouds and daylight across time zones to keep the target in view, confirmation is a gentle, formal moment. When the linked observations keep returning the same unbound solution, when independent teams see the same motion and measure similar brightness, the case becomes solid. The object earns a provisional tag. Then, if the orbit truly requires interstellar energy, it receives the I designation, and when the counting reaches it, a number 43I Atlas, that arc from first flagged frames to community follow-up to an orbit with eccentricity greater than 1 illustrates how faint lines in the dark become reliable knowledge. In the end, finding what barely glows is less about a single heroic exposure and more about rhythm and cooperation. Cadence reveals motion, linking turns motion into orbits, and follow-up transforms hints into certainty. Out of the hush of 1,000 quiet images, a traveler's story steps forward, a point of light that shifted just enough, often enough, to tell you it was passing through from somewhere else. Picture space as a landscape built from energy. The sun sits at the bottom of a deep valley, and everything nearby feels the slope that leads inward. A small body far away starts with some speed and some position in that landscape. Two simple ingredients tell its fate: kinetic energy, the energy of motion, and gravitational potential energy, the energy of being down in the valley rather than on the high plane. Add them together and you learn something profound. If the total is negative, the traveler is trapped in the valley and moves in a repeating loop. If the total is exactly zero, it rides the ridge and never quite falls back. If the total is positive, it crosses the ridge and keeps going into the next country. That single sign, negative, zero, or positive, decides whether an orbit is a closed poem or a one-line note. Escape velocity is the threshold between those stories. It is the minimum speed needed at a given distance from the sun to climb from the valley floor to the level plain without any extra push. At Earth's distance from the sun, that escape speed is about 42 kilometers per second. Earth itself circles at about 30 kilometers per second, which hints at the scale of the problem. Add enough speed in the right direction and a local object could break free. Direction matters, because velocities are vectors. A boost opposite to Earth's motion helps. A boost the wrong way may not. Escape is not a single magic number everywhere either. Closer to the sun, the valley is steeper and the threshold is higher. Farther out, the slope eases and the required speed drops. Interstellar visitors like 3 Atlas approach with something extra in their pockets: a hyperbolic excess speed. That phrase means that even very far from the sun, before gravity has done much work, the object already has leftover motion relative to the sun. Imagine walking into a valley while still jogging across the plain. You arrive already moving. That preloaded speed makes the total energy positive from the start, which is why the path cannot close. The sun can bend the route and speed the traveler up near approach, but without some way to bleed off. Energy friction, atmospheric drag, or a well-timed engine burn gravity alone cannot capture an object whose account began in the black. The geometry of the track follows the physics like a shadow. The family of possible pairs in an inverse square gravity field includes circles, ellipses, parabolas, and hyperbolas, all called conic sections. Circles and ellipses are the bound shapes. Parabolas are the knife edge of escape, and hyperbolas are the open curves of passers-by. The number called eccentricity labels those shapes. 0 marks a circle. Anything between 0 and 1 marks an ellipse. Exactly 1 marks a parabola. And greater than 1 marks a hyperbola. An open curve that comes from infinity and returns to infinity when the measurements of position and time are fitted, and the solution demands an eccentricity comfortably greater than 1. The sky has written the verdict in its own geometry, unbound, close to the sun. Conservation laws do the quiet, heavy lifting. Angular momentum is conserved, which means that as the distance to the sun shrinks, the speed must increase so that the product of distance and sideways motion stays constant. You can picture a figure skater drawing in their arms to spin faster, then extending them to slow down. Energy is conserved too, aside from tiny non-gravitational nudges like gas jets. As the traveler falls inward, potential energy becomes kinetic and the speed climbs. After the turn, kinetic energy flows back into potential as it climbs out again and the speed falls. Without a mechanism to dissipate energy, the book balances perfectly. The object departs with the same hyperbolic excess speed it had on the way in. Only the direction has changed. Why does the path bend at all if escape is guaranteed? Gravity focuses the motion. The sun pulls inward a little more strongly at closest approach, turning the track by an angle that depends on how fast the object is moving and how near it passes. A slow approach allows a wider turn. A fast approach yields only a modest deflection. Either way, for positive total energy, the curve is open. The traveler arrives from one side of the sky, swings around the sun, and heads away to the other side, like a stone that glances off a curved shield. Asterisk. Could anything make the path close? In principle, yes. But nature is stingy with those circumstances. A spacecraft can fire a rocket and dump energy as exhaust. A comet diving through a thick atmosphere could lose energy to drag, although that would be a very dramatic end. A near miss with a massive planet can either boost or reduce heliocentric energy depending on geometry through a gravitational assist. Capturing an interstellar body into a bound orbit that way is possible in theory, but requires a particular alignment and timing, and even then the odds are small. For a modest visitor on a quiet sun-skimming arc like 3 Atlas, no practical breakweights along the road. The escape idea also explains a few familiar numbers. Earth's escape speed from Earth itself is about 11 kilometers per second. That is the speed a spacecraft needs from near the surface if it wants to leave Earth for good. But ships aiming for the deep interplanetary dark need more, because they must also climb out of the sun's valley. That second climb is why the 42 kilometers per second figure matters for heliocentric escape at Earth's distance. Spaceflight uses gravity assists and carefully timed burns to cheat the bill. Rocks and ice do not get to choose, which makes their fates beautifully honest. If all of this feels a little abstract, an everyday picture can fix it. Think of a skateboarder in a smooth halfpipe. Start from low and push gently, and the motion repeats in a loop, left and right, an ellipse in wood. Start from exactly the lip with just the right speed, and you skim the edge and never drop back. Parabolic escape. Start with more than enough energy, and you fly out of the bowl, touch down on the far pavement, and keep going, a hyperbola in shoes. Gravity is the curve of the ramp. Energy decides whether the motion echoes or departs. For 3 Atlas, the minimal physics says this much, and it is enough. The total energy of motion and position is positive. The measured eccentricity sits above 1. The track bends, but does not close. Near the sun, the pace quickens, then eases with distance, and no invisible tether pulls the arc back into a loop. The universe allows many kinds of journeys, and this one is a graceful pass-through. A single bow to the sun followed by the long road back to the wide, cold plain. Draw a calm line across the night, and imagine it bending gently around the sun. That is the path of 3 Atlas, plotted not on paper but in space itself. The geometry is almost head-on to the solar system's usual traffic. Its orbit is retrograde, tilted by roughly 1, so it comes in against the general direction of planetary motion, like a quiet cyclist gliding along the edge of a slow parade in the opposite lane. That odd angle is a clue in plain sight. This traveler is not from here. Timing gives the second clue. The visitor was first flagged in early July of the year 2025, out beyond 4.5 astronomical units from the Sun, and its course leads it inward to a single close solar pass in late October. That moment, called perihelion, comes at roughly 1.2 astronomical units from the Sun. a touch inside the average path of Mars. The shape of that turn tells the story of its freedom. The curve bends neatly and then opens again. Speeds rise and fall along that arc the way a skateboarder quickens at the bottom of a smooth ramp. Far out, 3 Atlas cruisers. Nearer the Sun, it accelerates. After the turn, it eases away. Near perihelion, estimates place its pace at roughly 68 kilometers per second. A number you can also read as about 245,000 kilometers per hour. Those are honest speeds, earned by gravity, the natural outcome of sliding through the Sun's well on an unbound path. Safe distance, meanwhile, is not a vague comfort. It is geometry. For Earth, the closest approach is widely separated. On this pass, calculations put the minimum distance at no nearer than about 1.6 astronomical units, with mid-December bringing a gap of around 1.8 astronomical units, roughly 270 million kilometers. That is, comfortably farther than the Sun is from Earth. A line that distant is a line without peril. The same story holds for Mars. The visitor's road threads the region near Mars's orbit. But even there, the separation is measured in tens of millions of kilometers. Forecasts suggest an early October miss distance of about 30 million kilometers close by cosmic standards, far by human ones. Think of 2 ships passing on opposite sides of a wide bay, visible to each other, entirely untroubled. Why safe is truly safe comes from 3 simple facts that play well together. First, the distances are large and well constrained by many nights of position measurements. Small tweaks to the orbit solution do not erase hundreds of millions of kilometers. Second, the object's total energy with respect to the Sun is positive, which means it is not looping back through our neighborhood. It is a single guest, not a repeat visitor. Third, the planet's gravity can deflect, but not magically grab and redirect a fast, unbound traveler onto a collision path without an extraordinarily precise and unlikely alignment. The quiet math of conic sections and conservation laws leaves very little room for drama. There is also the practical question of seeing it, because the closest solar pass happens a little inside Mars's average distance. The glare of the Sun will wash over much of the show for casual eyes. Even so, telescopes both survey sentries on the ground and instruments in orbit can follow the changing brightness and color, sorting out what is geometry and what is surface activity. For patient amateurs, the object will likely remain a dim prize, more a plotted point than a spectacle, but it is present all the same. Writing numbers we can read. If you like anchors, keep these in your pocket. 1 astronomical unit is the Earth-Sun distance. 3 Atlas never comes closer to Earth than roughly 1.3 of that. The perihelion is roughly 1.2 astronomical units from the Sun, with the moment arriving in the last days of October. Near that turn, it runs at about 68 kilometers per second, and the plane of travel is tipped by about 100, a near mirror to the planet's direction, which is why its track slices across our sky rather than drifting along with the crowd. Each figure is a soft bell rung by repeated measurements, not a single shout. In the mind's eye, then the route is simple and elegant. From the deep outer dark, the traveler draws near. It curves around the Sun once at a heedful distance and glides back outward, leaving Earth and every planet far to the side. A single line, carefully measured, becoming a quiet assurance. This is a passing hello, not a problem to solve. Asterisk. Think of a very slow, very quiet firework. There is a small spark at the center, the solid nucleus, and around it, a faint expanding haze. That is what astronomers look for when they ask whether a visitor like 3 Atlas is active. Activity simply means sunlight is warming surface ices enough to release gas, which lifts dust into space. The gas is invisible in ordinary photographs, but the dust reflects sunlight, turning a single star-like point into a soft blur with sometimes a tail. From that blur, measured carefully, you can learn a surprising amount. Brightness is the first clue, and astronomy keeps score with magnitudes. On this scale, smaller numbers mean brighter things. A drop of 1 magnitude corresponds to roughly 2.5 times more light, while a change of 5 magnitudes is about 100 times. It feels backwards at first, but the system is wonderfully practical in a typical observation. A telescope records the visitor and a handful of nearby comparison stars in the same image. Because the stars' magnitudes are well known, you can calibrate the newcomer's brightness against them, correcting for thin cloud or haze along the way. Distance shapes what those numbers do. Sunlight fades with the square of distance, so moving twice as far from the sun makes the available light fall by 4. The light then spreads again on the way to Earth, dimming with the square of that second distance. That is why comets often brighten steeply as they approach the sun. They are receiving more light, and if they become active, they present more reflecting surface as dust spreads around them. Many comets brighten faster than pure geometry predicts, often roughly as the 4th power of the sun-to-comet distance, because dust production increases as more ices sublimate. The exact rate varies from object to object, but the principle holds. Closer, warmer, dustier usually means brighter. Whether a haze appears at all depends on which ices are present. Water ice needs stronger sunlight and typically becomes vigorous inside about 3 astronomical units. Carbon dioxide and carbon monoxide can sublimate farther out, even beyond 5 astronomical units, stirring a coma when water would still be asleep. If an interstellar traveler carries volatile ices near the surface, activity can begin early and stay gentle. If its top layer is crusty or depleted, it may remain star-like until much nearer the sun. A true coma is more than a blur. It has a characteristic shape. Close to the nucleus, the surface brightness often declines smoothly with distance from the center, a signature of steady dust outflow. Astronomers check this by comparing the object's profile to nearby stars. A star blurred only by the atmosphere and optics has a tight point spread function. A comet with a coma has a profile that is wider and shallower. If the blur is real, measuring how much wider it is helps separate the dust light from the nucleus light. That separation matters because a bright coma can make a tiny nucleus look deceptively large. Tails add another layer of information. A dust tail curves gently, shaped by sunlight's pressure. An ion tail often looks straighter, guided by the solar wind and pointing almost directly away from the sun. Tails do not trail behind the object like a scarf in the wind. They point away from the sun regardless of the direction of travel, which is why a comet can appear to have its tail ahead of it when geometry demands, when the sun-object-Earth angle lines up just right. Forward scattering by fine dust can make the whole scene brighten dramatically, a kind of optical silver lining dot. Activity is not just a picture. It is also a force. Gas jets act like tiny thrusters, producing accelerations too small for the eye, but large enough for precise orbit fitting to notice. If the measured positions keep deviating in a consistent way from a purely gravitational path, non-gravitational terms are added to the motion model. Detecting that nudge is strong evidence that gas is escaping, even when the coma is faint. Those same jets can torque the nucleus, speeding up or slowing down its spin over weeks or months. In extreme cases, spin-up can pull a loose object apart. In milder cases, it simply changes the timing of the light curve. Flicker. Color and spectra turn brightness into chemistry. Through broad filters, many dusty comets look slightly reddish, a hint of complex organics and weathered grains. With spectrographs, faint emission bands from fragments like cyanogen and hydroxyl can appear, tracing gas production. Even when an interstellar visitor is too dim for detailed spectroscopy, color indices, simple differences between filter scan, suggest whether the dust grains are coarse or fine, and whether the surface is neutral or reddened, because activity can masquerade as size. Astronomers use careful tricks to estimate the nucleus. High-resolution images may reveal a sharp central peak, the point-like nucleus inside the broader coma. By modeling and subtracting the coma's expected profile, you can back out the likely brightness of the solid core and place limits on its diameter. There is also a handy shorthand for dustiness, called AF-rho, said like a fro, which condenses albedo, dust production, and the size of the measuring aperture into a single number with units of length. Bigger values generally mean more dust in the coma. It is not a perfect measure, but it lets observers compare results from different nights and telescopes on a common yardstick. Sometimes activity hides. A body can be shedding gas that is too tenuous to glow strongly, or the dust grains can be large and dark, making the coma low in contrast. In those cases, variability becomes the clue. If the brightness undulates with a rhythm that does not match the expectations from distance alone, rotation and patchy jets may be at work. Conversely, a steady geometry-driven brightening without extra fuzz suggests a quiet, possibly rocky surface, or an icy surface protected by a mantle of dust. All of these pieces, profiles, colors, small orbital nudges, combine into a personality sketch. A soft, expanding haze and a dust tail imply accessible ices and a surface that yields to the sun's touch. A near-stellar profile with a clean light curve suggests a crusted or inactive exterior. A forward scattering surge hints at fine grains, while a stubbornly reddish color points to weathered dust. None of these signs taken alone writes the full biography, but together they turn faint fireworks into a readable message. For a traveler like 3 Atlas, the message is the prize. Activity, if present, tells of composition and texture formed under another sun. The way the coma grows, or fails to grow, hints at how its surfaces aged during a long drift in the cold. The tiny pushes of escaping gas, recorded in the mathematics of its path, whisper about vent locations and spin. Even when the whole show is little more than a smudge and a line, the light is eloquent. With patient measurements, the night sky yields its quiet, quantitative poetry. Asterisk. Picture a snowball with tiny steam vents turning slowly in sunlight. Each vent exhales gas that acts like a miniature rocket, nudging the snowball in whatever direction the vent points. That is the essence of non-gravitational motion for an active, cometary body. When ice near the surface of 3 Atlas warms and sublimates, escaping molecules carry momentum away. Dust grains hitch a ride and add a little push of their own. None of these pushes are dramatic. They are gentle, steady breaths. But across weeks and months, they shift the track enough that careful measurements can feel the difference. Astronomers describe the direction of these nudges in a simple local frame tied to the orbit. One axis points directly away from the Sun. One lies along the path of motion, and one is perpendicular to the orbital plane. A push away from the Sun slightly alters how near or far the object falls at each moment. A push along the path acts a bit like a tap on the accelerator or brake, changing the timing and stretching or shrinking the size of the orbit solution. A push out of the plane tips the path, tilting the track by small angles that add up over time, even if gravity dictates the broad hyperbolic sweep. These small thruster-like effects can fine-tune where the traveler appears by night. How strong are the pushes? Typical accelerations, inferred for active small bodies, are tiny, many millions of times weaker than Earth's gravity at the surface, and only a very small fraction of the Sun's pull at the same distance. Think of the weight of a feather resting on a moving train. The feather cannot steer the train, but under the right circumstances, it can be measured pressing on the window. The effect grows when activity is vigorous and fades when the vent's quiet. Composition matters too. Water ice becomes lively nearer the Sun, while carbon dioxide and carbon monoxide can work farther out. So the same object may be more responsive at one part of its passage than another. Turning those ideas into numbers requires a model. The classic approach is to keep gravity as it is and add 3 small terms, one for each local axis, scaled by a smooth function of solar distance that represents how sublimation tends to rise and fall. The scaling can be tuned for different ices, a water-like curve that brightens inside a few astronomical units, or a carbon monoxide curve that activates earlier. Fit the model to the astrometric positions, the precise sky coordinates, recorded at exact times. The software solves for the tiny coefficients that best reduce the residuals, the little differences between predicted and observed positions. The path to that fit runs through the details of observation. In each image, the target is not a crisp dot. It is blurred by air and optics into a point spread function. If a coma is present, the light can be a touch wider than a star's and slightly lopsided. That lopsidedness can bias the measured position toward the brighter side, subtly shifting the photocenter away from the true nucleus to mitigate that. Teams modeled the profile, compare it to nearby stars, and use small apertures or specialized fits to keep the centroid honest. Because different telescopes and cameras have different quirks, solutions usually give less weight to outliers and ask for agreement across instruments. Before declaring a real non-gravitational signal, outgassing does more than push. It can twist. Vents located off the spin axis exert torques that speed up or slow down rotation. Over weeks, the rotation period may drift by measurable amounts. In extreme cases, surface patches can shed material, altering the light curve. A changing spin can in turn change which areas receive midday warmth, moving the active patches and reshaping the thrust pattern. That feedback is why some comets show asymmetric behavior before and after closest approach to the Sun. The same real estate is not being heated in the same way on the outbound leg. Not every nudge comes from gas. Sunlight itself pushes on dust and on very low-mass, high-area surfaces through radiation pressure. For large, compact nuclei, this is negligible. But for fine grains, in a coma, and for unusually light, flaky fragments, the effect is real. Thermal forces can matter for bare rocks. As a small, dark object warms on its afternoon side and re-radiates heat, the recoil can slowly shift its orbit, a process known as the Yarkovsky effect, for an active, dusty traveler like 3 Atlas. Outgassing is expected to dominate while the ices are lively, with radiation pressure mostly sculpting the dust tail rather than steering the nucleus, because the signals are tiny. Uncertainty deserves a gentle, honest seat at the table. Star catalogues used to calibrate images carry their own errors. Atmospheric, seeing changes from minute to minute. A trail that is slightly smeared can move the centroid by a fraction of a pixel dot to handle that kindly. Orbit solvers propagate a full covariance mathematics that tracks how uncertainties in one measurement relate to uncertainties in others, and they test the solution by removing a night's data and refitting to see if the result holds. Independent teams using different pipelines and telescopes act like a truth squad. When several groups recover the same small acceleration with compatible values, confidence grows. Another useful habit is to allow the thrust pattern to shift with time. Some models permit the peak activity to lag behind the moment of closest approach to the Sun, reflecting thermal inertia in surface layers. Others split the scaling into inbound and outbound halves, recognizing that dust mantles can grow and choke vents as the object evolves. These refinements are not for decoration. They keep the model physically plausible while remaining simple enough that the solution does not chase noise. What does a detected nudge imply? First, it is evidence for escaping gas even when images look nearly stellar. Second, the direction and strength of the fitted terms hint at where vents might sit and how the object is spinning. A strong push away from the Sun suggests dayside sources. A strong push along the path hints that the warmest vents face a little ahead or behind local noon. Third, the total thrust budget tells something about how much material is leaving the surface. Small in absolute terms, but meaningful over the timescale of a passage. There are also helpful negatives. If positions remain perfectly gravitational within the measurement noise, that does not prove the surface is inert. It simply sets an upper limit on any jetting. If color and spectra show no obvious gas features, activity could still be dominated by large dark grains that are hard to see. And if different teams recover slightly different small the cause may be mundane differing apertures, different seeing, or varying coma structure on different nights. In the end, non-gravitational modeling is less a dramatic reveal and more the art of listening for a whisper while an orchestra plays. Gravity takes the lead and writes the main melody. Outgassing radiation and thermal effects add faint harmonies that, once heard and measured, make the whole piece clearer. For an interstellar visitor like 3 Atlas, those gentle pushes turn brightness and chemistry into motion, letting a quiet smudge of light disclose its vents, its spin, and a fragment of the landscape from which it first learned to breathe. Asterisk. Every new visitor invites comparison. 3 Atlas, the third in the short ledger of confirmed interstellar objects, naturally draws glances back toward 1I, Oumuamua, and 2I, Borisov. Each carried its own quiet lesson, and together they sketch the range of what such travelers may be. Oumuamua, discovered in October 2017 by Pan-STARRS, was the first. It entered from the direction of Lyra, curved around the Sun inside Mercury's orbit, and departed on a hyperbolic path. It showed no obvious coma, which surprised many. Its brightness rose and fell dramatically, suggesting an elongated shape or perhaps a flat one, tumbling through space. Some speculated wildly about sails and artifacts. The calmer view sees a natural fragment, maybe a shard from a disrupted planetesimal, coated or crusted enough that little gas escaped. The absence of a visible coma did not mean the absence of forces. Careful measurements showed that its path deviated slightly from a purely gravitational track, consistent with a tiny non-gravitational push. The simplest explanation is outgassing at levels too faint to brighten the images much, but enough to nudge the orbit. Borisov, discovered in August 2019 by amateur astronomer Gennady Borisov, was the second. It behaved very much like a classic comet. It displayed a clear coma and a generous tail. Spectra revealed the fingerprints of familiar ices. It looked, in many ways, like the long-period comets of our own system only. Its orbit told the interstellar tale. With an eccentricity greater than 3, Borisov's activity made it easier to study composition. Measurements showed it was unusually rich in carbon monoxide relative to water, hinting at formation in a colder region of its parent system. The tail stretched in graceful agreement with solar pressure and wind. Compared to Oumuamua, Borisov was less mysterious, but no less precious. Proof that interstellar traffic includes icy comets as well as enigmatic, inert-seeming shards. Now comes 3 Atlas. Early reports suggest it. 2 has a cometary appearance, faint but real. That places it closer to Borisov's family portrait than to Oumuamua's, but its tilt, timing, and detailed behavior remain its own. Each of the 3 points to a different corner of possibility, one dry or crusted, one lively and icy, one intermediate and awaiting full story. The pattern is already instructive. Interstellar wanderers are not a single type. They are a mix, reflecting the diversity of their birthplaces and the chance processes that freed them. Some are dark and compact, others dusty and active. Some carry more carbon monoxide, others less. The ledger is small, but the message is large. Nature exports many varieties. The comparisons extend to speed and direction. Oumuamua approached at about 26 kilometers per second relative to the Sun from a high galactic latitude. Borisov arrived at around 32 kilometers per second, also from a tilted trajectory. 3 Atlas brings its own hyperbolic excess, arriving at roughly 25 kilometers per second before the Sun's pull accelerates it near. The precise numbers differ, but the shared truth is that all carried more than the local escape energy, and all cut across the solar system's regular lanes rather than joining them. Brightness and detectability also vary. Oumuamua was faint and discovered late, already outbound. Borisov was brighter, active, and noticed inbound, allowing longer study. 3 Atlas, with survey coverage improving year by year, was flagged months before perihelion, giving observers the chance to plan. That progression speaks less to the objects themselves and more to our growing vigilance. When myths creep in, it is usually through the open door of rarity. The first interstellar visitor inspired speculations about alien engineering. The second was more familiar but still rare enough to stir exotic theories. By the third, the pattern is settling into science. The myth gives way to the mundane wonder. These are natural fragments, born under other suns, set free by dynamics, and passing us by. That does not make them less marvelous. It makes them more. It means the galaxy is not sealed. Material crosses between systems. The stuff of one nursery can, across eons, pass by another. It also means that with enough vigilance, we will gather a sample large enough to test real distributions. How many are crusted shards? How many are icy comets? What chemistries appear common and which are rare? How do their surfaces weather the long cold, and how often do they carry volatiles that sublimate far from any star? Comparisons sharpen those questions. One without a coma tells you that crusting or depletion is possible. One with a rich coma tells you that Essos can survive the drift. A third with modest activity suggests middle ground. The myths fall away, but the poetry remains. Each traveler is a messenger. Oumuamua whispered about shapes and crusts. Borisov sang of ices and tails. 3 Atlas writes its note in light curves and faint haze. Together they spell a single word. Variety. Variety is science's favorite word because it opens doors. Variety means we can measure distributions instead of anecdotes. Variety means we can ask about origins rather than exceptions. Variety means the next discovery will not close the story, but widen it. So 3 Atlas stands not only as a singular object, but also as a bridge between the first, lonely data point and a future ledger where interstellar visitors are common enough to map. A bridge between speculation and statistics. A bridge between myth and measurement. Asterisk. Origins invite curiosity. How does a small body find itself unbound from its home system and wandering into the galaxy at large? The story is not exotic. It is the quiet arithmetic of gravity and time. Picture a planetary system in its youth, filled with leftover planetesimals, icy and rocky bodies that did not grow into planets. The newborn giants, still migrating, scatter these leftovers with each encounter. Some are pushed inward to burn or collide. Some are nudged outward to long elliptical paths. A fraction receive just the right shove to exceed, escape speed and drift away forever. That fraction becomes the seeds of interstellar traffic. Once set free, they keep moving on straight, wide arcs, carrying the composition of their birthplaces. Over billions of years, the galaxy fills with these quiet exiles. Most never pass close to another star. A few do. An even smaller number happen to glide close enough for instruments like Atlas to notice. Ejection is efficient. Models of our own solar system suggest that Jupiter and Saturn together have likely expelled more small bodies than remain bound. Every massive planet in every system does the same work, clearing its neighborhood by feeding some inward, parking some in distant reservoirs, and launching some outward to infinity. So when 3 Atlas appears, it is not an isolated miracle. It is one mote in a galaxy already seeded with trillions of such wanderers. The rarity lies not in existence, but in encounter. Space is wide, and only a handful of these arcs bring a guest into telescope range in any given decade. From that perspective, each detection is not the beginning of the phenomenon, but the continuation of a very long process. The night sky simply provides a stage for us to notice what dynamics have been writing since the first systems formed. Could an object also be set free by gentler processes? Yes, star clusters, where suns are born close together, allow tidal nudges and encounters to exchange material between siblings. Binary stars can share and shed comets across their shared gravitational field. Over galactic timescales, even weak stellar flybys can stir the distant reservoirs of comets and send some drifting away. But the dominant mechanism is still the simple kick from a giant planet. That is why variety is precious. A crusted shard like Oumuamua might be the fragment of a disrupted larger body. An active comet like Borisov may be a survivor from the outer belt of another system. A faintly hazed traveler like 3 Atlas may record intermediate histories. When we say interstellar, then we are not talking about deliberate journeys. We are talking about exile's natural consequences of planetary dynamics. They are debris made into messengers. The chemistry they carry is chemistry from elsewhere. Dust grains, Isas, organic soil are frozen samples from environments beyond our sun. To read their light is to peek at recipes written under different conditions of temperature, pressure, and stellar color. Each encounter, therefore, widens perspective. The early solar system is not unique in making comets. Other systems do the same. Other suns fling out messengers of ice and rock, and in time, some of those messengers cross our path, writing brief streaks in our ledger before fading back into the dark. Future instruments will lengthen that ledger quickly. The Rubin Observatory, with its wide field and deep nightly scans, is expected to notice many more interstellar visitors once fully operational. Its sensitivity will reveal fainter, smaller bodies that surveys like Atlas might miss. With each detection, the statistics sharpen that the European Space Agency's Comet Interceptor mission is even designed with this possibility in mind. It will wait in space for a suitable target, perhaps a long-period comet from our Oort cloud, perhaps an interstellar traveler. If the latter, humanity may send cameras and instruments directly to greet a visitor from another sun. Think of that progression. First faint dots in survey images, then catalogued orbits, then chemical hints from light curves, and one day direct flybys with resolved images, from myth to measurement to encounter, all within a few decades. Origins, then, are not mystery but arithmetic, and futures are not silence but preparation. 3 Atlas stands in the middle, reminding us that every small visitor is the product of long dynamics, and every detection is a rehearsal for richer meetings to come. Hold the thought gently. The galaxy is full of these travelers. Most pass unseen. A few cross the lens of human instruments, and each one, in its faint whisper of light, carries the story of another sun's restless nursery. Asterisk. The new instruments preparing for those future encounters deserve a calm moment in the light. The Rubin Observatory, on a mountain in Chile, will conduct a legacy survey of space and time. Each clear night, its wide mirror and giant camera will sweep broad sections of sky, producing a rolling movie of change. Stars that vary, galaxies that flare, asteroids that crawl all will be captured. Among them, faint interstellar wanderers will be noticed earlier and in greater numbers than ever before. The key is cadence and depth. Rubin's exposures will be deep enough to catch faint objects and repeated often enough to spot motion. What Atlas and Pan-STARRS can do today, Rubin will do with much more reach, covering most of the southern sky every few nights. That combination means that instead of a surprise every few years, interstellar discoveries could become annual or even routine. Routine does not make them dull. It makes them useful. With a catalogue of dozens or hundreds, astronomers can map size distributions, spin states, chemical fingerprints, and velocity patterns. They can test whether our solar system's ejected debris looks typical or unusual compared to our neighbors. They can ask how many fragments look crusted, how many are icy, how many reddened by organics, how many shaped oddly by collisions. Another step forward comes from missions already in planning or flight. ESA's Comet Interceptor will sit in a quiet orbit near the L2 Lagrange point, 1.5 million kilometers from Earth, waiting. When a new, interesting comet is flagged, perhaps even an interstellar one comet, Interceptor will launch from its waiting spot and fly by, taking images and spectra from close range. The mission design is clever. By not targeting a specific body in advance, it stays flexible, ready to intercept whatever promising traveler appears during its operational years. That agility is exactly what interstellar science needs, because you cannot schedule when a new guest will arrive. Other spacecraft, like NASA's upcoming Near-Earth Object Surveyor, are also optimized to find small, faint bodies, mainly for planetary defense, but with the side benefit of cataloging the unexpected. Together, these instruments form a quiet promise. The third interstellar object will not remain lonely for long. Science grows by accumulation, but wonder grows by contrast. Each visitor reminds us that our solar system is not an island. Material moves between stars. Debris trades hands across the galaxy. A fragment of another nursery can, across eons, draw close enough that we can measure its light and sketch its nature. The myths fade, but the reality is more generous. We do not need sails or artifacts to marvel. A small, natural fragment, born under another star and set free by gravity, is marvel enough. Its path is a line in our sky, but its story is the long history of planetary systems everywhere. When you next look upward, imagine one of those faint lines still unseen. A traveler drifting quietly across the dark. Somewhere in the galaxy, one is already on its way, invisible now, destined to be flagged by a survey in a year or a decade. And somewhere in orbit, an instrument may one day turn to meet it face to face. That is the gift of 3 Atlas, the third entry in the ledger. Not just a visitor, but a reminder that there will be a 4th, a 5th, a 50th. Each will bring its own accent, its own chemistry, its own whisper of origin. Science waits patiently, instruments awake in the dark, ready to notice the next guest. And we, meanwhile, can rest in the quiet assurance that the sky is larger, stranger, and more generous than habit suggests. The story ends where it began, with a question for the pillow. What secret does a traveler from another star leave behind when it passes only once? The answer is not a single number or a single line, but a collection of gentle truths. It leaves behind geometry written in motion. It leaves behind chemistry folded into color. It leaves behind the certainty that systems like ours are not alone in making such fragments. And most of all, it leaves behind the sense that the universe is porous, connected, and kind enough to let one nursery's dust drift through another's. That knowledge, soft and sufficient, is enough to close the eyes upon. So let the mind rest. The stars will keep their watch. And somewhere, even now, another traveler is on its way. Quietness is a clue. A modest coma, or none at all, tells of crusts and Isas held tightly. A broad hazy veil says Isas are shallow and sun-warmed. Jets that push hard enough to shift the orbit whisper of vent patterns and surface textures. Colors hint at dust chemistry. Together, those signals are not just decoration. They are the fingerprints of another planetary nursery, carried across the gulf to our sky. Allow the mind to hold one last image of scale and honesty. The sun's gravity shapes an elegant valley. Inside, the planets loop forever, tied by negative energy. At the ridgeline sits Escape, where orbits open. 3 Atlas crosses that ridge with a positive balance. It bows to the sun, speeds up near the turn, slows again with distance, and leaves. That simplicity does not reduce wonder, it refines it. The wonder is not in speculation, but in clarity. An object born under another star, seen here and measured, obeys the same quiet rules. Gravity, energy, and light curves write the story without need of embellishment. The story has already settled into place, like dew on quiet grass. A safe distance, a line that does not close, a modest brightness, a coma and perhaps a tale, a name that carries its discovery, and a place in a very short ledger. 3I Atlas, the third interstellar visitor, recognized in time to follow inbound, watched as it curved around the sun, and noted as it faded again. Each fact is gentle, but together they mark a milestone. The third time proves the category real. It shows that the galaxy is open, that debris moves between nurseries, and that our instruments are now awake enough to notice. What remains is the patience to add more entries. Instruments already wait in darkness. Rubin's nightly sweeps, comet interceptors watch. Space telescopes checking for moving dots all are rehearsals for the next guest. Some will be bright and dusty, some dark and hard, some rich in carbon monoxide, some quiet and crusted. All will be natural, and all will carry stories of formation and scattering elsewhere. So the narrative is not an ending, but an invitation. 3 Atlas comes, bows, and goes. The sky assures us there will be a fourth and a fifth, and science assures us that each will widen the ledger until the variety itself becomes the message. Until then, the quiet is enough. A single line drawn across the sky by a traveler from another star. A modest coma, a safe passage, a hyperbolic orbit, a story legible without myth. That is a sufficient lullaby. Rest easy then in the company of travelers. The stars keep their vigil, the surveys keep their cadence, and somewhere out there another faint dot already drifts toward discovery. Asterisk. Imagine again the scale. The Earth and Moon span a pocket ruler. The Sun is 400 of those away. The outer planets are tens of those long strides beyond. The Oort cloud, if it exists, stretches tens of thousands of those steps, a fragile halo. Beyond that, the galaxy is seeded with debris from every nursery. Each piece a shard of history. 3 Atlas is one of those shards. Its path is not a loop, but a crossing. Its eccentricity is greater than 1. Its energy positive. Its light is modest but measurable. It is neither a threat nor a spectacle, but a data point of profound importance. That data point tells us something simple. Planetary systems are not closed. They leak. Giants fling leftovers outward, and the galaxy becomes a commons where each system leaves traces of its youth. The night sky is not only stars but also fragments in motion between them. The imagination is tempted to make them artifacts or messages, but the real message is already generous. Natural fragments are enough. They prove connection. They prove commonality. They prove that the physics of scattering, migration, and escape are not unique to us. To see one is to confirm many. The first was rare. The second showed variety. The third confirms pattern. That pattern is now part of astronomy's quiet map, alongside planets and stars, nebulae and galaxies. There are interstellar wanderers, a new category that bridges systems. Consider how discovery changes with time. Once, only bright comets near perihelion were noticed by chance. Then came patient visual searches. Now come robotic sentries scanning nightly. Soon, Rubin will extend the reach so that faint fragments are noticed earlier and catalogued faster. Each technological step has shortened the delay between event and recognition. That shortening matters because it opens the chance of direct encounter. A spacecraft at rest at L2 can be told, months in advance, to pivot and prepare for an intercept. The chain runs from faint dots in survey frames to orbit solutions, to an alert to a launch toward a moving target. If one of those targets is interstellar, we will meet a piece of another system up close. Cameras will see texture, spectrographs will see chemistry, dust analyzers will taste grains. The leap from speculation to direct evidence will be short. All of that begins with the patient discipline of noticing faint dots that move. Without Atlas, without Pan-STARRS, without Zwicky, without the global network feeding the minor planet center, no orbit would be known, no interstellar designation assigned. The modern miracle is not technology alone, but cooperation. Astronomers across continents and longitudes extend arcs, cross-check measurements, and refine orbits. Amateurs contribute confirmation images. Professionals model residuals. Agencies approve designations. The quiet, distributed effort turns whispers into knowledge. 3 Atlas is a case study in that process. A survey spots it. A center posts it. Observers confirm. Models fit. The orbit settles. The eccentricity proves unbound. The designation is granted, and the story is told. So the interstellar ledger grows, not by accident, but by design. Human vigilance has matured to the point where faint interlopers cannot pass unseen. That, as much as the physics of hypervalis, is the story worth resting on. Each visitor, faint though it may be, becomes a mirror. In its light curves and spectra, we glimpse not only its own surface, but also echoes of our own beginnings. The dust that drifts from its coma resembles the dust that once drifted in the solar nebula. The ices that sublimate under sunlight echo the ices that once fed our comets. The lesson is not that we are unique, but that we are common. If 3 interstellar visitors in a handful of years can show such variety, then every star must be launching debris of many kinds, endlessly. The galaxy is a conversation of fragments, a slow exchange of crumbs from distant kitchens. For planetary science, these encounters are gold. They allow tests of models that otherwise remain abstract. Computer simulations predict ejection rates, volatile survival, and fragment sizes. Each real visitor checks those predictions. Are most interstellar bodies small or large? Are they icy or rocky? Do they redden with age in deep space, or do they retain bright surfaces? Each answer sharpens theory. For astronomy more broadly, they prove that local dynamics matter on galactic scales. The scattering by a single Jupiter can send material out into the Milky Way's shared commons. Our own system has likely contributed its quota of messengers, invisible to us but present in the dark between the stars. 3 Atlas is simply reciprocity, another system's leftovers, drifting past our lantern. There is also a philosophical comfort. The loneliness of space softens when you recognize that material is exchanged. Not messages, not crafts, not intentional artifacts, but the honest dust of formation. It is enough to know that what we see tonight once orbited another star, was warmed by another sun, and now leaves a single trace here before continuing. Future generations may collect samples. If an interstellar comet comes close enough, spacecraft could be dispatched to gather grains from its tail, returning to Earth a piece of another system's chemistry. Even without that, dust detectors on existing craft may one day register a high-speed particle whose trajectory reveals an interstellar origin. In tiny fragments, the chemistry of alien nurseries may literally fall into our instruments already. Interstellar dust streams are measured flowing through the solar system. Grains a few microns across detected by satellites. They hint at larger cousins, comets, and asteroids on hyperbolic tracks. The continuum from dust to comets confirms that systems do not end cleanly at their edges. They blur into the shared medium of the galaxy. So when we watch 3 Atlas fade, we are not closing a book, but opening a chapter. Its brief glow is one data point in a distribution that will, with time, become rich. That richness will tell us not only about 3 Atlas, but about how common our own story is in the wider Milky Way. For now, the task is simpler. Measure carefully, report honestly, fit orbits, check residuals, share data. The discipline is the same as it has always been. Patience with faint signals. From that patience, the profound emerges. Asterisk. Imagine again the valley of the sun's gravity. Within it, planets circle endlessly, comets dive and return, asteroids wander. But some paths come only once, cresting the ridge with extra energy and never falling back. 3 Atlas is one of those one-time paths. Its eccentricity greater than 1 is not an abstract number. It is the clean statement that its energy balance is positive. No loop is possible. The shape of the orbit is a hyperbola, an open curve that approaches, bends, and departs. The mathematics is exact, but the picture is simple. A stone skimming a pond, leaving ripples, not circles. In this case, the ripples are faint light curves, coma profiles, residuals in orbit fits. They are the evidence that a fragment from another nursery crossed our view. Even the uncertainties are instructive. When orbital fits include non-gravitational terms, when profiles are compared to stellar points, when colors are measured across filters, the error bars remind us that nature is subtle. The object is faint, the atmosphere imperfect, the detectors noisy. Yet from those faint signals, knowledge emerges. It is a kind of discipline. Trust the signal. Admit the noise. Report the error. That honesty is part of the lullaby. Nothing is exaggerated, nothing overstated. A small visitor passed. It was measured. It was unbound. That is all, and it is enough. Think of the chain of effort behind that modest conclusion. Engineers building survey telescopes, programmers writing pipelines, observers checking confirmation pages, amateurs contributing follow-up, professionals fitting orbits, committees assigning designations, writers recording results, each part necessary, each part quiet. Together, they turn faint dots into stories. Without the chain, 3 Atlas would remain only a passing, unnoticed smudge. With the chain, it becomes the 3rd interstellar object, part of science's permanent record. This process itself is comforting. It shows that vigilance works, that cooperation spans borders, that patience yields truth. In a world noisy with speculation, astronomy's quiet cadence offers steadiness. So let the thought rest here. A faint object, measured carefully, fitted honestly, named clearly, compared gently, placed in a ledger and released. That is the whole story, and it is as complete as any lullaby needs to be. Consider the ledger now. 1 I, Oumuamua, 2 I, Borisov, 3 I, Atlas, 3 lines, 3 distinct portraits. The first, a shard without a coma, tumbling oddly. The second, a lively comet with tails and gas. The third, modest, cometary but faint, clear in its unbound motion. 3 lines are not a full book, but they are enough to shift perspective. They prove that interstellar visitors are not accidents. They are the natural outcome of planetary dynamics everywhere. They show variety, which means the category is broad. They demonstrate that surveys are capable of catching them. Already, theorists adjust models. Predictions for size distributions, for chemical ratios, for ejection rates. Each is checked against the 3 cases. Each case suggests refinements. Maybe crusting is common. Maybe icy comets survive well. Maybe fragments span a wide range. Future cases will fill the gaps. Some will look like asteroids, some like comets, some like hybrids. Some will be bright enough for spectroscopy, others too faint for anything but some will pass close, some far. Each one will sharpen the statistics. That is the horizon science sees now. Not one mystery, but a distribution to measure. The ledger will grow from anecdote to catalogue, from wonder to routine. In routine, clarity emerges. The galaxy is seeded with fragments. Systems shed debris. We are simply beginning to notice. For the wider world, the romance remains. News of an interstellar visitor still stirs imagination. But for science, the comfort is that imagination is no longer needed. The facts are enough. The objects are real, the orbits secure, the physics clear, and yet the poetry lingers. To say a traveler from another star passed through is not diminished by clarity. It is enriched. The truth itself is the marvel dot. So the ledger, small as it is, carries weight. Each line is a chapter in a book that is only beginning. Each visitor is a lullaby sung across light years, noticed briefly, unfolded into memory. Think of the galaxy as a slow circulation. Stars are born, live, and die. Planets form, migrate, and scatter. Comets are stored, perturbed, and ejected. Across billions of years, debris trades places, drifting between systems like pollen on a breeze. 3 Atlas is a grain of that pollen. Its presence confirms that the circulation is real, not just theoretical. We are part of a galaxy where material moves. There is a humility in recognizing scale. This body may be a kilometer or 2 across. Its journey has lasted millions of years. Its notice in our sky will last months. Against those numbers, human urgency softens. The rhythms of the galaxy are slow, and they do not mind our haste. That very slowness is a gift. It means the sky is not fragile. It means visitors come and go whether or not we watch. Our role is simply to notice, to measure, and to learn. And so we close with perspective. A 3rd interstellar object has been measured. It has a safe distance. It has a hyperbolic orbit. It carries the chemistry of another nursery. It is modest in brightness, but generous in implication. From here, the work continues. Surveys will find more. Instruments will improve. Missions will be sent. The ledger will grow. Each line will be another reassurance that we are not alone in process. That other systems scatter fragments just as ours does. That the galaxy is connected by quiet, natural messengers. For now, let the thought be simple. 3 Atlas came. It was seen. It was measured. It is leaving. That is enough. Hold one last image before rest. Picture the sun as a lantern in a wide cathedral. Around it, the planets move in patient orbits, bound by invisible ribbons of gravity. Into this cathedral walks a guest. It bows politely, curves its path in respect, and leaves through the far door. It does not join the dance. It does not stay. That is 3 Atlas. The bow is geometry. The respect is energy conservation. The leaving is the definition of unbound. Nothing more is needed. Nothing less is true. In its light are hints of color. In its orbit, the proof of origin. In its faint haze, the whisper of chemistry. Together, they are the signature of a world we will never see, a system far away whose dynamics once tossed this fragment into the galaxy. That signature is the only gift the traveler leaves. It is enough. Enough to measure, enough to compare, enough to remind us of scale comforts. Earth is a pocket ruler from moon to sun. The solar system is a long walk in astronomical units. The galaxy is a garden seeded with debris, and a fragment only kilometers across can cross that garden and pass by us. Noticed briefly, then gone. This perspective is the lullaby. Our lives are short and urgent. The stars are long and patient. The visitors are few, but they come. And in their coming, they remind us of continuity. Systems form, scatter, and share. Debris drifts. Surveys watch. Science records. Wonder lingers. 3 Atlas is the 3rd. There will be more. Their ledger will grow. Their statistics will sharpen. Their chemistry will be catalogued. Already the path is clear. Already the future instruments wait. Already the night sky holds other fragments inbound, invisible for now, but destined to be noticed. Rest in that knowledge. The universe is porous, systems share, fragments travel, and we are awake enough to see. The stars keep their vigil, whether we watch or not. The surveys keep their cadence, whether we notice or not. But when we do notice, when a faint dot is recognized as a traveler, something shifts in our sense of belonging. We are reminded that our system is not an island. We are part of a current, a drift of fragments across the galaxy. 3 Atlas is only one mote in that current, but it is enough to illustrate the truth. Planetary systems shed pieces. Those pieces travel. Some of them, by chance, cross our sky. The record is modest. Discovery date, positions, magnitudes, orbit fit, designation, comparisons. Yet in that modesty lies weight. The numbers are precise, the orbit unambiguous, the implications wide. What more is needed for wonder? Not speculation, not embellishment. Only the calm recognition that matter from another sun drifted here, that our instruments were patient enough to see it, and that our science was steady enough to write it down. Such recognition is the very heart of astronomy. To notice, to measure, to understand, to let go. The stars remain. The fragments continue. Our role is only to witness, and in witnessing we find peace. The sky is not empty. It is full of connection, not in messages, but in matter, not in deliberate signals, but in the quiet sharing of debris. That sharing is enough. So the story closes where it began, with a question. What secret does a traveler from another star leave behind? The answer is simple and soft. It leaves behind a line in a ledger. It leaves behind a trace of light. It leaves behind the certainty that the galaxy is open and generous. Let that be the lullaby tonight. A traveler came, was seen, was measured, and departed. Another will follow. The universe is wide, the stars are many, the fragments uncountable. We are here to notice them for a moment, then rest. Allow the mind to settle with one last image of scale and honesty. The sun's gravity is a valley. Inside it, the planet's loop, bound by negative energy. At the crest lies escape, where orbits open. 3 Atlas crossed that crest. It bowed, curved, and left.